This webcast talks about how to calculate and quantify the amounts of mechanical energy that either redistribute within a system or are transferred to or out of a system. So we're talking about mechanical energies, which we've talked about before. Mechanical energy is due to position or motion or both. And the primary forms of mechanical energy are gravitational potential energy, elastic potential energy, and kinetic energy. We will also talk about dissipated energy, which is unusable, unrecoverable, microscopic kinetic energy, most commonly due to friction. Okay, so e.g., gravitational potential energy. This is energy that a system has because the object is elevated. It's above the Earth. The typical convention is that a system has zero gravitational potential energy when it is on the Earth's surface. And as the object gets raised higher above the Earth, the gravitational potential energy increases. Here are the formulas for calculating gravitational potential energy. On the left is a snapshot. If you would like to know at this moment what is the gravitational potential energy of this system, then you'll use this equation, where the Eg equals the mass multiplied by g, which is the acceleration due to gravity, and also multiplied by the height above the Earth. Okay, so mgh gives you the gravitational potential energy at that moment. Sometimes, though, we also talk about a change in the gravitational potential energy, and that would be equal to the mass times g times the change in height. And when we talk about a change in height, we always take the final height minus the initial height. Let's go calculate a couple of types of gravitational potential energy. So I'm going to worksheet 6F. I'm going to look at problem 1 here, where we're talking about a physics binder has a mass of 3 kilograms sitting on a classroom table. That is the situation. So we're going to determine Eg for different positions of the zero reference level. So here we're saying, so here's the table, and here's the book sitting on the table. Here we're saying that the table itself is where we say height equals 0. That's our reference level. Well, the physics binder is sitting at that height. So the gravitational potential energy would be its mass times g times the height. But in this case, it's at the 0 reference level. And so it would be 0 joules, since by definition, height is 0 because of the way it's been defined. What if then we said that the reference level, so it's exactly the same situation. The book is sitting on the table, but now we're saying that on the floor is where height is 0. And so the book is sitting on the table, which is 0.68 meters above the floor. So the gravitational potential energy would be its mass times g times that height. So we've got 3 kilograms as its mass, 9.8 newtons per kilogram is the acceleration due to gravity, and the height is 0.68 meters. So now the Eg for this book would be 3 times 9.8 times 0.68, which is 19.992 joules. So same situation, but since we have set a different value of the 0 reference level, the book has a different amount of gravitational potential energy. What if, we still have the table with the book sitting on it, but now we're saying that the reference level of 0 is set at the ceiling, which is 2.5 meters above the table. So now the book is actually 2.5 meters below that reference level. So now the gravitational potential energy would be its mass times g times the difference from that height. It's below the reference level, so its height is negative 2.5, and so we would actually have a negative gravitational potential energy of negative 73.5 joules. So gravitational potential energy can be negative. It's usually positive because usually we have the ground as our zero reference point, and we are talking about things above the ground. But if you talked about going below that level into a hole or a mine, going below the Earth, then you are talking about negative gravitational potential energy. Let's take maybe a more common example. Here we've got a squirrel, also 3 kilograms, and it descends from the top of a 50-meter high tree to a branch that's only 2 meters off the ground. So we're talking about the change in the gravitational potential energy. That would be the mass times g times the change in the height. So I need to take the final height minus the initial height. Okay, the mass is 3 kilograms, g is 9.8, and here the final height is 2 meters, but the initial height was 50. And so the change in gravitational potential energy is going to be negative 1,411.2 joules. Okay, let's go talk about a different type of energy. Let's talk about elastic potential energy. So this is energy that's stored in an elastic object because that object is undergoing a reversible deformation. The energy is stored until the force is removed and the object is allowed to spring back to its original shape. Objects that are deformed but do not bounce back are not storing elastic potential energy. Okay, so here are the equations for elastic potential energy. On the left is the equation if you would like to know at this point of time, at this moment, how much elastic potential energy is in this elastic object. That energy is equal to 1/2 times the spring constant, K, times the square of the displacement. And we have seen in previous worksheets, sometimes we could talk about a change in elastic potential energy. Perhaps you had an initial displacement of the spring, but then you changed that displacement. You stretched it further or compressed it further. And if you wanted to talk about the change in the elastic potential energy, it would be equal to 1/2 times the spring constant times the final displacement squared minus the initial displacement squared. Let's go look and calculate a couple of elastic potential energies. So I'm back at worksheet F, and let's look at problem 6 and 7. So here in problem 6 we've got a bungee cord. Bungee cord is an elastic object. You can stretch it and it will bounce back. And here it says that the bungee cord has stretched 25 meters, so that is the displacement of this bungee cord. It has a spring constant of 140 newtons per meter. It's very common to talk about elastic objects as if they were springs. Okay, so they've given us a spring constant for this bungee cord. We'd like to know how much energy is stored in the bungee cord. This is kind of a snapshot calculation. Right now, while it's stretched 25 meters, how much energy is stored in it? So to calculate that elastic potential energy, I need to take 1/2 of the spring constant and multiply that by the square of the displacement. So 1/2 times the 140 newtons per meter times the 25 meters squared. And we would see that it's 43,750 joules. Let's do one more of elastic potential energy, number 7 here. It says how much energy is stored when a railroad car spring is compressed 10 centimeters. So the displacement is 10 centimeters, which is 1/10 of a meter. And it says the spring requires 10,000 newtons to be compressed 3 centimeters. That puts me in mind of Hooke's law, which says that the applied force equals the spring constant times the displacement. And they're telling me that the applied force has to be 10,000 newtons if the displacement is 3 centimeters, which is 0.03 meters. And so I could solve for K here. And I get quite a large K, because this is for a railroad car, 333,333 newtons per meter. Okay, so now that I want to know energy stored, I'm going to use the elastic potential energy equation. The energy stored is 1/2 times that spring constant times the displacement squared. I'm sorry, it was 0.1 meters. It was 10 centimeters or 0.1 meters. And so let's see here. And so I get an energy stored of 1667 joules. Okay. Let's go back, and so we've talked about the two types of potential energy, gravitational and elastic, but now let's look at kinetic energy. So kinetic energy is energy that an object possesses because it is in motion. And so that as speed increases, kinetic energy increases. And here are the equations for kinetic energy. On the left is the snapshot. At a particular moment, the kinetic energy is equal to 1/2 times the mass of the object times the square of its velocity. And if you want to talk about the change in kinetic energy, it will be 1/2 times the mass times the final velocity squared minus the initial velocity squared. Notice that I'm subtracting the squares of the velocities. I'm not taking the difference between the velocities and then squaring that difference. It's very important to look at this formula. Let's go back to the worksheet and look at a couple of these with kinetic energy. So let's look here at number 3. How much kinetic energy does a 2,000 kilogram SUV have if it's going at 70 miles per hour? So this is snapshot. I'm trying to find the kinetic energy right this minute. Kinetic energy would be half of the mass of this SUV times the square of its velocity. Now, one thing I have to pay attention to, this is not in standard units, so I'm going to convert this miles per hour into standard units, which would be meters per second. They're telling me that 1 mile is 1,600 meters, and I know that an hour is 3,600 seconds. And so let's see here. So always work in standard units. That gives me 31.11 meters per second. Okay, so I've got 1/2 times the mass, which is 2,000 kilograms, times this 31.11 meters per second squared. And so I get 967,901 joules. That's the kinetic energy of that SUV at this moment. because this is talking about a change in kinetic energy. And so, because this truck slowed down from 28 meters per second to 8 meters per second, the change in kinetic energy is 1/2 times the mass times the final velocity squared minus the initial velocity squared. Now I have to be careful here because I see something that is not in standard units. It's a 14 megagram. Let's just think about that. That's 14 times 10 to the 6 grams, because mega means times 10 to the 6, but the standard unit for mass is the kilogram, and there are 1,000 grams in 1 kilogram. So really this is 14,000 kilograms, right? 14 times 10 to the 6, 14 times, that would be 14,000 kilograms. Okay, so 1/2 times 14,000. The final velocity here is 8. The initial velocity is 28. So I take final squared minus initial squared, and let's see what this is. So I'm going to get a negative number. Because the truck slowed down, its kinetic energy got smaller. So the change is a negative number. Negative 5,040,000 joules. Okay. Let me just talk about one other type of energy, which is dissipated energy. This is energy that is wasted because it is used to excite individual atoms and molecules, and so it represents unrecoverable, unusable, microscopic kinetic energy, energy that we cannot move back into any other storage modes, so we won't be able to use it for useful work. Okay, usually this is due to frictional forces. It can also be due to air resistance or loud noises, the creation of light, things like that. Here are the equations we can use to calculate energy dissipated by friction or air resistance. Notice that the equations are very similar. In both cases, the dissipated energy equals the force times the path length. The path length is important. The longer that you slide a box across the floor, the more friction has to be overcome. So the dissipated energy equals the friction force times the path length. Similarly, if something is moving through air or some other liquid and encountering and a drag force is opposing it, the dissipated energy is equal to that drag force times the path length that it moves through that fluid.